Hello, my name is George Wynne. I'm a PhD student at Imperial College London, and this is the video for my talk at Kernel 2 sample test for functional data at the second Symposium on Machine Learning and Dynamical Systems. This is joint work with Andrew Duncan, who's also at Imperial College. So a quick overview of this talk. We're going to be talking about what is a two-sample test, what is functional data, and what do kernels have to do with it. So first of all, what is a two-sample test? To establish a notation, calligraphic X with the underlying space for which our probability measures are over. Calligraphic PX is going to be the space of Borel probability measures, and P and Q are going to denote two different measures, or potentially different measures. We're going to take some samples from them. So XIs are going to be a collection of IID samples from P, and YIs an IID sample from Q. We want to perform a test with controlled error using this observed data, and the null hypothesis is that P is equal to Q, and the alternative is that P is not equal to Q. This is a very much classically studied problem with some decades-old work having gone into it. And the idea of this method is that this piece of work is that we're going to be dealing with this when our data is functional data. So what does functional data mean? In our case, our calligraphic X is going to be some infinite dimensional space of functions, in particular a real separable Hilbert space. So for example, L2 over a compact subset of RD. So each xi or yi is going to be a function, and examples of random functions are, for example, trajectories of SDEs or Gaussian processes. In practice, we'll only observe discretized versions of these things because in the real world, we only observe a finite number of observations of random functions. And we could be in a scenario where they are somehow dense, and everything we need to compute about these functions, for example, integrals, we can do so because we've got loads and loads of observation points for each random function. However, if they're not observed somehow densely, but somehow sparsely instead, then we're going to have to fit curves to them. So the special thing about functional data is that we know the underlying space is actually an infinite dimensional space. So we have to take into consideration things we know about infinite dimensional distributions, for example, Cahunan-Liouville expansions. But then we also have to deal with the statistical impact of fitting curves to these discretized observations. Now, that naturally begs the question, why not just treat our observations as a finite dimensional vector? For example, imagine for each random sample, or each random function, we observe it at 20 locations. So you could say, well, why don't we just treat that as a 20-dimensional vector and use a finite dimensional test? And the issue there is that, first of all, assuming that every random function, each xi, for example, is actually observed at the same locations and the same number of locations is a non-trivial assumption already. So that might be out the window to begin with. Secondly, if you treat it as a vector, then you lose all sense of that of these samples actually being functional. So then you can't really incorporate things like knowledge about the Cahunan-Liouville expansion. If you have knowledge about the periodicity, if you have knowledge about change points of the distributions or the smoothness, you can't use any of that. And finally, if you are using a finite dimensional test, then that test, the behavior of that test as the observation grid gets finer, means that the dimension of your observed vector gets higher. And sometimes finite dimensional tests, as the dimension increases, the power decreases. So some existing approaches for two-sample tests for functional data mostly rely around reducing the problem to a finite dimensional problem, or computing empirical quantities that are to do with the principal components. So, for example, this reference here projects the signals to finite dimensions using functional principal component analysis, FPCA, and then employs a bona fide finite dimensional test, the Anderson-Darling test. This reference here will compute the empirical estimates of the principal components and then use statistics based around those, but will only compute up to a certain number of principal components. That threshold has to be chosen as well. And this final one, it represents a characteristic function-based approaches where you make empirical estimates of the characteristic functions and then do distances between them. The kernel approach that we'll be using does not have to do this finite dimensional projection, and it doesn't have to compute empirical versions of functional principal components. And this is the main reason that they, in our numerical simulations, result in higher power, because it doesn't have this extra added layer of estimation before you do the test. So what is the kernel approach? The main idea is to map P and Q into some different space and then form a statistic based on the distance in that space. So the work of statistical kernel methods, in particular two-sample tests, has reached quite a mature state in the last 10 to 15 years. And for this reason, a lot of the theory has been wrapped up for it, but mostly in, almost exclusively in finite dimensional cases. So it leaves a hole for functional data to be using these methods. A kernel, K, will have two inputs, and it's a positive definite symmetric function. The mean embedding is defined as follows. I'm missing out some very basic technical assumptions about boundedness, but these are satisfied by all kernels used in practice, really. So mean embedding phi kp is this guy here, and this is a member of the RKHS of HK. So the maximum mean discrepancy is the distance between these two things in the RKHS. Now, by virtue of the reproducing property, in fact, before we carry on, we should mention that this is not necessarily a distance between P and Q. This is not necessarily a proper distance on calligraphic PX, because the kernel needs to be characteristic. And a kernel being characteristic means that this embedding here is injective. This is not always the case. Now, numerous kernels on our D have been shown to be characteristic. For example, the very popular Gauss kernel and the Matern kernel here. But most proofs of this characteristicness require local compactness, which is not the case when X is an infinite dimensional Hilbert space, and this will be the main scenario. By virtue of the reproducing property, if we square the MMD, we can write it in multiple different ways. For example, there's an integral probability metric, which makes it more comparable to standard or more classical measures of distance on probability measures, for example, Wasserstein distance, because instead of having a unit ball in the RKHS, you'd replace it with the unit ball of a different function space. The main thing here is that we can write it as these double integrals, and these can be easily approximated using a Monte Carlo approximation given our samples. And this is how the estimator for our test is formed. We'll use this thing here, which is based on the kernel evaluated at our points we've observed. So our test statistic, we use bootstrap to work out the test threshold and reject or accept our null hypothesis if it is above or below the threshold. The computational cost of computing this thing is ON squared, where N is the number of samples, but there is an ON estimator, but it has higher variance, so lower test power. So the contributions of our work is to harness these kernel-based methods, which have seen great success in machine learning for finite dimensional problems, and use them for functional data problems. So the main technical challenge of doing this is making sure you have characteristic kernels over these infinite dimensional spaces. So we will define a broad class of characteristic kernels when X is an infinite dimensional, real, separable Hilbert space. Then, once we know that MMD is a metric, we can investigate its theoretical properties, for example, the topology it induces. And finally, we can give conditions to alleviate the statistical impact of curve fitting in the test. What this means is that we can make statements about how many observations per curve, discretized function sample you need to effectively reconstruct the sample, and then when you use the test based on this reconstruction data, the null hypothesis of the limiting distribution of the estimator has the same limiting distribution as if you had access to the true underlying sample. So let's start with defining this broad class of kernels. The main idea is that there is yet another form of MMD one can use. If your kernel is equal to the Fourier transform, also known as the characteristic function, of some measure mu, then using the double integral representation of MMD and Fubini's theorem, you can write it as a weighted L2 distance between the characteristic functions of P and Q here. So we've got the distance here squared, and it's weighted by mu. This is why mu is known sometimes as the spectral density of K. So this might look like a bit of an esoteric object. However, by Bochner's theorem, for every kernel K that is continuous translation invariant on our D, there is such a mu. So for example, the Gauss kernel, mu will be a centered Gaussian distribution. Now it's easy to see that if mu has full support, then the MMD between P and Q is 0 if and only if P hat equals Q hat. So the reason for this is if MMD is 0, and if mu has full support, then p hat and q hat must equal each other almost everywhere. But as p hat and q hat are continuous because they are Fourier transforms of measures, then they must be equal to each other. And Fourier transforms of measures are injective, so if p hat equals q hat, then p must equal q. Therefore, MMD is 0 if and only if p equals q, and this means that k is characteristic. So this proof, we can actually go ahead and generalize to infinite dimensions, because the formulation of a characteristic function is naturally done for a real separable Hilbert space. And the key idea is to use as a base to define a family of kernels the infinite dimensional generalization of a Gaussian distribution on Rd to get a kernel. And the generalization of a Gaussian distribution on Rd is a Gaussian measure. And in particular here we're going to be using a centered Gaussian measure. So whereas on Rd a Gaussian distribution has a covariance matrix, on X, which is a real separable Hilbert space, we'll have a covariance operator. So it's an infinite dimensional version of a matrix. And the formula for the characteristic function of a Gaussian measure with covariance operator C is given here. So this looks like the Gauss kernel if C was the identity. But the identity is not a valid covariance operator for a Gaussian measure, but I'll talk about that later. What's interesting to note is that a covariance operator has a spectral decomposition. So these lambda ends are eigenvalues and the E ends are eigenvectors or eigenfunctions of the operator C. And E ends will form an orthonormal basis. The lambda ends are greater or equal to 0. And this measure has full support if and only if C is injective, which is also equivalent to these lambda ends all being strictly positive. So, by the argument on the previous slide, C is injective if and only if this guy has full support, and then that happens if and only if then the K defined here is characteristic. So that immediately gives us a family of kernels over X which are characteristic, specifically the characteristic functions of Gaussian measures which have injective covariance operators. So how can we get examples of injective covariance operators? Well, the really easy case is to take some K0, some kind of base kernel, which is on whatever underlying space your functions might have. So if your functions were in L2 over 0, 1, K0 will be a kernel on 0, 1, and defining the corresponding integral kernel operator here. And then if K0 is integrally strictly positive definite, which there are lots of examples of, then C will be injective. So this is the preliminary argument, but this can be extended by using limits. So such allowable C here have to be trace class, but by using a limiting argument, you can get this to hold for operators which are the pointwise limits of trace class operators. And this is summarized in the theorem here. Let X be a Polish space, which is actually more general than a real separable Hilbert space. And Y a real separable Hilbert space. T will go from X to Y, be a continuous and injective map. Then what we are calling the squared exponential T kernel here is characteristic. So this is a really wide family of kernels, and I'm going to talk about some examples now. So if Y equals X and T is C to the half, then we recover the characteristic function we talked about just before. If Y equals X and T is the identity, this gives us a Gauss-like kernel here. But we might use T to be a bit more of an exotic map. So what might we do? Here we can actually make T map to the Cartesian product of two spaces. So we have now two terms here. And this one has these squared terms which will actually emphasize the second order information about the signals. So if you're wanting to do a two-sample test, but rather than an arbitrary difference of distribution, you wanted to only measure difference in covariance structure, which is quite common in functional data analysis, then this will be a kernel you might want to use because it emphasizes the second order information. And then more generally, T can be chosen to emphasize certain parts of the signal by using spectral decompositions. So in our paper, we give a general recipe and some examples about how to choose T from principal point of view and such that the resulting kernel is still characteristic. A quick aside is that, and this is expanded more in the paper too, is that for some choices of T, the SET kernel, squared exponential t kernel, can actually be expressed in this interesting formulation here, which we call the integral kernel framework, where k0 is some kernel on R, and n is going to be some measure on X. And this framework actually makes it, easy conditions can be given on k0 and n to ensure that this is a characteristic kernel. And you can actually construct other kernels from this framework, which you wouldn't have been able to do if you'd been working only with the characteristic function of Gaussian's framework, as mentioned before. For example, you can actually derive a inverse multi-quadric type kernel here, which is also characteristic. Now I'll discuss some properties of MMD. So we know that when using a characteristic K, MMD is a metric on Px. So it would be a metric on probability measures over an infinite dimensional space. So this begs the question, what topology does it induce? And are there some closed form solutions for common combinations of P, Q, and K to get to grips with how this metric behaves? So here's a straightforward theorem about MMD. So let X be a Polish space and K a bounded continuous characteristic kernel. And if Pn here is a sequence and converges to some P, that's in Px, weakly, then MMD will converge to 0. And on the other hand, if this is tight, so it's a tight sequence, then MMD converging to 0 will imply that Pn converges weakly to P. The proof of this involves the double integral representation of MMD in terms of the kernel, and the tightness is used to compensate for the lack of local compactness of X. So this tightness assumption isn't actually needed for finite dimensional cases. However, it's still an open question if there are some specific kernels for which the tightness can be relaxed. And in terms of closed forms for certain P, Q, and K, on our D, we know that we can obtain closed form for the MMD between two Gaussian distributions when we use a Gauss kernel. And since the Gaussian measures on X, i.e., for example, Gaussian processes, and the SET kernel are natural infinite dimensional generalizations, we may obtain closed forms for them too by using the standard identities for Gaussian measure integration. And I'm not going to list them here because it would introduce some notation, but please, I encourage you to go look at the paper and see them. They are exactly what you'd expect if you have a look at the finite dimensional version. And then if you knowing that you can write a Gaussian process using the KL expansion, you take the limit of the finite dimensional version and you'll end up with our results. Also, closed forms for the variance of the MMD estimators can also be derived this way, which can be helpful for investigating the power of the test. Okay, so now we're ready to talk about curve fitting of the discretized random samples. So we'll first establish our notation. Remember that xi and yi were the random samples from P and Q, and now calligraphic I will denote an information operator, and it will map to an n, capital N, dimensional space here. So a classic example is when I is pointwise evaluation at a set of n points. And then we will use R to denote the reconstruction operator, which will take that information and map back into our space calligraphic X in an attempt to approximate the true samples. So Ri X sub I will be attempting to approximate X sub I. And the idea is that to compensate for this discretization, we're going to need to require n, the dimension of the information we observe, so for example the number of points, to grow with little n, the number of samples, and for the information and reconstruction pair to give good enough approximation so that the distributions that will make our threshold for the test using this reconstructed data will match the true distribution of the threshold if we had the true data. So we're going to formalize this in a theorem here. So K will be the squared exponential T kernel that we defined before. And then X sub n will denote the set of points xi that are from P, and yn, y's from Q. And we're going to assume that P is not equal to Q here. So this would be our alternative hypothesis, but an analogous result holds the null hypothesis. And these are the reconstructions, and they're going to be based on n, capital N, dimensional discretizations, and this will depend on little n. And the conditions here are to say that the approximations have to be good enough in expectation. Okay? And good enough means that they have to decay at least as fast as n to the minus half. Then we see here that we have the MMD based on the reconstructed data, and then this limiting distribution is the same as if the MMD was based on the true data in the case of our alternative hypothesis. Again, an analogous result holds the null hypothesis, where the MMD based on the reconstructed data will have the same distribution as the MMD estimator based on the true samples with no discretization. So this shows us that as long as our approximation is good enough, and this is a very broad condition here, because we're not actually making much intrinsic assumptions on R or I, we just need the approximation here to be good enough. So we can give a very simple example of this, and we give more examples in the paper. So the most basic example is using a piecewise interpolant. So now we're going to give an example on what things actually very clearly satisfy those conditions. So first of all, we're going to imagine our space is L2 over 0, 1. And our information operator is just pointwise evaluation on some grid of capital N points, we'll call them the TIs, where their distance between each one is reciprocal to the number of points we have. Then, based on this data, the reconstruction operator is going to be the piecewise interpolant, given by this formula here. And now we just need to assume that P and Q have some regularity here, and this will allow us to get the convergence rate for the error of approximation here. So given we have this regularity, it's a classical result that the piecewise interpolant would have this sort of error here, where it's the square reciprocal of the number of points, and this here is a constant given our assumptions on P and Q here. So if the number of points here is asymptotically the same as n to the alpha, with alpha at greater than a quarter, then this term here would be less than n to the minus half, so the condition from the theorem will be satisfied. So this gives a very simple example of how these conditions of the theorem are not very restrictive, and it also shows the interplay between the reconstructions and the regularity of the samples and the number of points. So here we've assumed more regularity of the samples, and we don't have to use as strong a reconstruction here, and therefore we don't need as many points per function sample. Okay, so that wraps up the 3 main points. I'm just going to quickly discuss some of the things that are covered in the paper. There is an investigation into the limiting scale, as I mentioned, increases of finite dimensional tests, 2-sample tests. So this is if you take your functional data and just pretend it's a finite dimensional vector, what happens as you take more and more discretizations. And we show that it naturally converges to a kernel that's defined over functions. Also, we talk a much more depth about a programming framework to construct these T's that are used in the squared exponential T kernel, and how to incorporate the knowledge about the signals to result in more powerful tests. Then we have a numerical section which compares to existing functional data analysis 2-sample testing methods and shows that we gain superior power. And we think this is mostly because the reasons we mentioned earlier. Upon using kernels, we don't have to be computing like empirical functional principal components or things like this. And doing such a framework, when you do have to compute empirical functional principal components, you have uncertainty and variability there, and then do a test based off that, decreases the test power. So I want to say thank you very much for listening. And we believe that the intersection of statistical kernel methods and functional data analysis really is in its infancy. Statistical kernel methods over the past 8 to 10 years have shown great results in machine learning and become a very helpful tool, an established tool there. And we believe that with some of the framework we've set up here, we can incorporate more knowledge and more theory we have about functional data and incorporate this into these kernel methods to get very good and well performing tests, and for other statistical kernel methods too. Here are the references that I discussed earlier, and thank you very much for watching.